Hi, and welcome to this first video in a sequence of videos on recurrent neural networks. So in this video, we'll just motivate these recurrent neural networks, and in the following videos, we'll go into details about how to train them and what considerations to have in mind. And so for this sequence of videos, it's assumed that you have already watched or at least know about neural networks and also how to train them. Okay. So the motivation for looking at these recurrent neural networks, if you want to do machine learning on sequential data, right? So for instance, here is a sequential data set, which basically measures or counts the number of airline passengers every month in a period of time from 1949 to 1960, right? And you can see clear sequential dependencies here, right? I guess if you know the past, it should be reasonably easy to predict the future of this sequence of airline passengers. Right, so the goal here is really to predict the number of passengers next month based on this historic sequential data. Okay. Another example could be stock prices. This is also sequential data, and maybe you have some historic development of the Google stock prices, and your goal is to predict the stock price tomorrow. And again, this is a sequential data set where time really matters here. Similarly, another type of sequential data that you could encounter or try to do machine learning on is text data, again, strings. This is really also sequential data consisting of words. Every single word is a step or data piece. And you might have variable length text sequences, and the goal might be, say, to predict the next word or to predict something based on this sentence. And so there are lots of sequential data out there. And how can we train to predict from sequential data where we try to exploit the sequential nature of the data? And I think the first natural thing to ask oneself is, could we just take some of these techniques and models and algorithms that we already know and try to adapt them to this sequential setup? And indeed we can. So I think it's very instructive to first think about how could we try to do this if we wanted to adapt the current models that we already have. Right, so let's try to do this just to motivate these recurrent neural networks afterwards. Right, so what we do is let's try to assume we're going to try and we have this variable length data, maybe this very long sequence of data, and we're going to try to fix a length of the sequences that we'll look at. So maybe we'll look at subsequences of this data, maybe consisting of 50 sequential data points or steps. Right, so in some sense, it means that we'll try to zoom in on a subsequence of length 50, a fixed length 50, and we'll try to take all the information that occurs in this subsequence as our features. Right, and then maybe the label when we use for training, if we're trying to predict stock prices, might be the price in just a step afterwards. Right, so that could be the label that we're trying to predict. And so then we'll basically have our long sequence and we can cut it into these many small sequences. And then the hope is, of course, when we want to make predictions, maybe we can kind of feed in the last 50 steps and try to predict the price of the stocks tomorrow. Okay, so in some sense, right, if we have this historic data already that's sequential, maybe we've gathered a bunch of information about every single time step, right? Maybe it's not just the price of the Google stocks, which is one feature. Maybe it's also the inflation. Maybe it's the stock price of Apple, and anything that we have measured that we think might influence the stock price of Google tomorrow. Right, so we have a bunch of features, and we have measured all these features for every time step. Okay, so the label we're trying to predict again is the stock price tomorrow in this example here. And it could be any type of information that we should predict based on these time steps that we've seen so far, the sequence we've seen so far. So the natural approach to try and modify existing algorithms would be say, well, I guess we have all this information from the previous days of the previous 50 time steps. We should, of course, feed this into the model, right? So what we'll do is we'll just create a very long feature vector. And then we'll take, I guess, all the features we have for step 1 in this subsequence, put it into the beginning of this feature vector, take all the information we have from step 2, put as the next features, all the information from step 3, put them as the next features, and so on, right? And we just concatenate all these, I guess, individual feature vectors of each of the steps into one very long feature vector that's 50 times longer than the features for every individual step. Right? That's a very natural thing to try and do. So maybe we can do this, right? And then we'll just feed it into, say, a neural network, which is one of the models we've seen previously. It could also be SVM or whatever, any of these learning models. Just put it in. Of course, this could work. just, I guess if we do it in a neural net, right, we'll have some of the input neurons will be, I guess, correspond to the step 1 features. Some of the neurons will correspond to the step 2 features. Some of them will correspond to the step 50 features, and so on. But let's try to discuss maybe what are some of the downsides of trying to do it like this. And in particular, right, this neural net will have a lot of features, weights in particular, right? This is if it's a fully connected neural net, right? Well, I guess we'll have this layer is like, if each step has D features, we have 50D input neurons, right? Which is, creates a lot of entries in this weight matrix, right? There's tons of entries. We have one row for every feature here, right? Now, the interesting or important thing to be aware of is if this is sequential data, you would think that each of these time steps should be treated kind of similarly, right? Because in particular, it's the same type of information that goes in. So really these different features that come from the different time steps, probably it's some kind of similar functionality that we need to learn for each of them. So if we really feed them in as 50 separate input neurons, then really we're forcing this neural net to kind of relearn the same functionality in many different places or parts of the neural net, right? So, which makes the learning task harder. Also, this really does not play very well with variable length sequences. If you always train on a length 50 sequences, if you feed in a length 49 or a length 51 sequence, it doesn't really adapt to this case, right? So there's a bunch of downsides in trying to do it like this. And this is really what motivates these recurrent neural nets that we'll see. So recurrent neural nets, what are they? Let's try to first look at just the high-level structure of recurrent neural nets. They're really just a variation on neural nets that are kind of tailored for sequential data. So the idea is that some part of the input neurons are allocated to the input features of a step. But the important point is that we don't have one batch of input neurons for each of the time steps. We only have like one place where we feed in the features, right? So think of it as that we have this batch of input neurons that takes in the input features of a particular step, okay? It has also output neurons, one or more, depending on what we're trying to learn, right? So we have output neurons up here. These will basically output in every single time step, they'll output a prediction. And this could be a single neuron if we're trying to predict, say, a value. So for regression type problems, it could be k different neurons if we're doing a classification task with k different classes and so on. Now, the special thing about these recurrent neural nets is that they also have, I guess you would call them output neurons as well, basically some kind of state that you want to send forward to step t+1 of the processing of sequential data. So there's some kind of state. And the main idea is that we'll feed this state back into the neural net. Okay, so this output of the neural net at step t will be fed into the neural net again in the next step. And let's try to give a little bit more details so we can kind of understand this functionality here. So let's go back to this example of Google stock prices. So at every single time step, right, what we've measured is the stock price of Google, inflation, stock price of Apple. Right, so we have these features measured for every single time step. And the labels that we're trying to predict is the stock price at the next time step. Okay, so what happens if we start processing the sequence, and let's start at step 1. Right, so in the very beginning, step 1. So for step 1, we measured the stock price of Google, say $1,210, the current inflation, 2.4, and the stock price of Apple, say 150. So we feed all of those into the input features for time step 1 here. So they fed into the neural net. It's recurrent neural net. Now, for the very first time step, so there's also this part of the input that is supposed to be the state from step t-1. In the very beginning, we feed in some kind of dummy fixed state. So let's just, for this example, say we feed in the zeros vector, right? Maybe other choices make more sense, but we'll just feed in the 0 vector here. Okay, so this comes in. And now what we do is this is a feed-forward neural net, right? So we process the neural net just as a standard neural network, and out comes a prediction here for what the stock price is in step 2. Right, so out comes a value here. And the interesting and non-standard part is that out of this neural net also comes a feature vector here that we in some sense want to forward to step 2. So this is a kind of state that we're outputting after processing step 1. So maybe this is the vector 2.4,7 that comes out. Okay, so now we finished processing step 1, and now we want to move on to step 2 here. And the interesting thing is that we now take this output, the state output, and this output of these neurons, we feed them back into the neurons here at the bottom. So now they're part of the input to the step 2 computation, right? So we replace this dummy computation now by this 2.4,7 that fed into these input neurons again. We moved on now to step 2. And for step 2, we also measured the stock price of Google, the inflation, and the stock price of Apple. And so for step 2, we have these features available, maybe 1235, 2.349. So we feed all of this into the input to the recurrent neural net, and we just repeat now. So we process the neural net as a feed-forward neural net. Out comes a prediction for the stock price at step 3. And out comes also a new state that we want to forward to step 3. So this is, say, 0.3, minus 1.2. So this is the processing of step 2. What we do now is that we take this vector here giving the state that we output, and we want to send it to the next step, and we feed it into the neural net again for step 3, right? So this is now the feature vector that comes in step 3 down here. Step 3, we again have features available from the sequence. We take those as input together with the state from the previous step, process it through the network, we get a prediction, we get a new state out of the network, and so on, right? So we feed again this output state into the network for step 4. We have the input features from step 4. We make the prediction, we get the next state, right? So I hope this is a clear description of how this recurrent neural net keeps feeding its state back into the neural net again for the next processing of the next state. So this is basically what recurrent neural networks are at the high-level structure. They have inputs that correspond to the D features of a single step. They don't input all the steps simultaneously. They produce output like standard neural networks, and then they have this special feature that they output also a state that they forward to the next step of the computation. So the benefits of this compared to a normal neural network is, in some sense, you have sharing of parameters across different steps of the computation, right? As you'll notice, right, there's only weights on these edges in the neural net, and these weights are shared amongst all the steps, right? So these input features that you get from every single step are passed through the same weight matrices, and the state that's passed through is also shared amongst them, right? So everything is shared across different steps of the computation, making the neural net have fewer weights and hopefully also being easier to learn. It can also process arbitrary length sequences, right? It produces an output every single time, so we can just keep going for whatever number of steps we have available and feed it all into this recurrent neural net. It has, in that sense, also the sharing parameters also means it has fewer of these weights than standard neural nets. And this has a special feature that you can forward state in some sense from previous steps of the computation to remember in some sense important information about this sequence that we're processing. Right, so what's coming in the next video is then how can we train these recurrent neural networks.